Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So thank you for coming. My name is Nicolás Villar. And I work as a researcher in the Microsoft Research Lab in Cambridge in the UK. And I'm part of a research team called Sensors and Devices, where we work at the intersection of, I guess, human-computer interaction, also ubiquitous computing, building systems that for people to use and to interact with. And there's a strong sort of hardware element to what we do. And what I want to talk to you about today is this project called .NET Gadgeteer, Microsoft.NET Gadgeteer. And what it is, the simplest way of putting it, it's a toolkit. It's really a set of tools that lets you go from having an idea about a device or a gadget that you want to build but it doesn't exist, and going from that idea to holding that device in your hand and using it as a real product. And what we've been trying to do is take that process from idea to reality in the quickest and easiest way we can. The driving principle behind designing this toolkit was to have something that has a low threshold. So basically, simple things should be easy to do, but also high ceiling. As you get more comfortable with the tools and you learn it, you can actually build sophisticated devices and complex systems out of it. And there's sort of three pillars that we thought are involved in making devices and that our toolkit addresses. One of them has to do with hardware, and so one of the pillars is modular hardware. The other one is object-oriented programming, making it easier and very productive to program these devices that you want to build. And the final one has to do with the design of the actual objects. And so the third pillar we called digital design and manufacturing. And what I'm going to do throughout this talk is go into detail about what each of these three pillars do. And then at the end I can show you how they all come together to sort of enable this ability to go from idea to high fidelity prototype in a very short space of time. But before I get into it, I just wanted to give you a little bit of history. The reason we originally built .NET Gadgeteer was as a tool for ourselves as researchers in the lab to quickly prototype and innovate and build devices. And we do this a lot because we believe that prototyping is key to innovation, to prove ideas, to test out what these devices are going to be like in practice. You need to build them, you need to make them work, and then you need to be able to give them to people, ideally a lot of people, for them to use in real-world scenarios. And then prove your ideas, and the quicker you can do this, the faster you fail, all the better. So you can prove good ideas quickly, but more importantly, discard bad ideas even more quickly. So we built this for ourselves, and we use it in the lab a lot to enable a number of projects. But since we built it and we've been developing it, we find that it's also been to interest of other researchers outside of the lab in academia. But also interestingly, a lot of hobbyists, people that at home like to build things for themselves, have seemed very interested in it, and also. Educators, people that teach programming and teach sort of design of interactive objects have asked us, could you make this available as an education tool? So because of this, we've been working very hard with colleagues from all around Microsoft for the last year and a half, getting this toolkit out of our lab and into the hands of other people. And at the end of the talk, I'll tell you a little bit more about how we're doing that. This is a list of a lot of the people that are actively working in that process. And you can see they can come from all across Microsoft. There's a couple of us in Microsoft Research Cambridge. There's also Carrie Hamill is in Microsoft Research Redmond. We're working very closely with the developer division, the people that make the programming tools, and you'll see some of the underlying technologies that we're using come from that division inside Microsoft. And we're also working very closely with Microsoft Research Connections, who's organizing this event, to try and get this out of the lab. So I'll go back to that first pillar that I mentioned, modular hardware. And this is when you're building a device, something that is not a computer, but it's interactive, it's a computing object, you need some electronics to power it. And we wanted to make it really easy, that without having any soldering skills or any knowledge of electronics, you can piece together a fully functioning device out of these hardware modules. So just to give you a little idea of how that works, this is just a quick example of building a fully functioning digital camera out of these modules. The thing that you see in the center is the core computing module, the mainboard that everything else plugs into. ¿Será que puede hacer clic? Gracias. So here I'm taking an SD card slot, somewhere I can store the photos when I build my digital camera, and I just connect it to the mainboard with this little ribbon cable. That's a small display, and that plugs into mainboard. Everything has these standard sockets that these little cables can plug into. So all the cables are the same, they're just different lengths. That's the camera module. And now I need a button to press to take the picture. So I'm just adding a very simple button module, an SD card to save the picture. And what's happening off screen now is I've written some code. It's not a lot of code, it's about 10 lines of code. I plugged into a computer, I'm programming it, and that's what's happening on screen. It's downloaded the code onto the processor, and it's executing on the processor. And there, I press the button, it shows it on the display, and it's saving it onto the SD card. That's a picture of me. So that's as easy as that's how easy it is to put the hardware together. So these are some of the existing hardware modules that we've built so far. The first one that you saw in the center was this mainboard, which contains the processor, the core processor, and some memory, and all these sockets that everything else plugs into. We have some user interface modules, buttons, slider, rotary encoders, the displays. This is a little display that I showed you, a much bigger display that you can with a touch screen, which is not shown here. And you can sort of swap all these things, little multicolor LEDs. We have sensor modules to sense things like colors, the color of the light, the distance to an object, ultrasonic sensor, temperature, humidity, accelerometer, and so on. Multimedia modules, the camera that you saw, we also have an audio module that lets you record and play back audio. Those is their communication modules. You can hook this up to Wi-Fi or Ethernet, or if you're building a sensor network, you can add an XB, a Zigbee, low-power wireless mesh radio module. Also serial line, if you are connecting this to a PC for data logging, for example. Storage modules, the SD card, USB host. You can actually, it's quite powerful. You can plug things like a keyboard or a mouse into this tiny computer and via USB, and it'll work. Actuator modules for robotics projects and things like that. We have a motor and controller. We have relays for interfacing with low and high voltage if you want to control items in your house. A researcher in a lab, his whole house is controlled. The heating in his house is controlled with Gadgeteer using these relay modules. Power supply modules, so if you plug it into a PC, it'll be powered from there, but these things are standalone. So we have battery modules that will allow you to, once you programmed and built a device, you just add a battery and it becomes a standalone battery powered device. And this, it's very important to point out, this is not a finite set. There's a lot, since I took this picture, we've built a lot more modules. We're planning to build a lot more. it's a very extensible in its nature, the design. We also have, if you have a sensor or something lying around the lab or a button that you want to connect, it doesn't have to be part of the kit. So we have other modules that allow you to interface to arbitrary electronics if you have the knowledge of how to do that. So that's the hardware, and as I showed you, you have all these modules, you have this sort of toolkit, you assemble them together very quickly, and the next step is you plug it into your computer and you program it. And the way that you program it is, it's actually quite comfortable. It feels more like you're programming a PC, that you're programming a little embedded device. If you have ever done embedded development on a small platform, you know what it's like. It's usually quite painful. And the reason it's so comfortable is because we're leveraging a great product called the Microsoft.NET Micro Framework. So I don't know how many of you are aware of the sort of the .NET framework is, the set of libraries that you use to program Windows, networking, and display, and all these things, libraries. And there's the compact framework that is meant to run on things like handheld devices, PDA, embedded devices. And this is the micro framework. This is the smallest of all of them, where it's really slim, and it can run on tiny devices like the small ARM7 processor that we have on our mainboard. As a result, because you're running the .NET micro framework on there, we can run managed code. You program it using Visual Studio and get all the debugging tools and everything that Visual Studio brings. And you write code in C#, which is a very productive and to my mind, a very nice language to program in. On top of that, we've built the Gadgeteer SDK, which makes it even easier to program these particular devices. So just to give you a little idea of this is kind of the standard stack of the .NET micro framework. You see, it can run straight on top of the hardware. You don't even need an operating system. So it has a very small footprint, and that's how you can fit it in a small processor. There's already a bunch of devices that are available commercially that run that .NET micro framework. It's not just Gadgeteer. You can go and buy these things nowadays, which sort of small embedded processors, and you program them in C#. It's great. But what we've done is we've added this Gadgeteer library on top of the .NET micro framework that makes it even easier to program these things. So for each one of those hardware modules that you saw, there's also a software module that makes it, there's a one-to-one correspondence between the two, and makes it really easy to use them. So if I press a button, I declare a new button in my code, and the button has a button pressed event and a button released event. It's hard to convey by a presentation, but if you have the chance to come to a demo tomorrow, I can give you a good idea of how easy really it is to program. Yeah, I can give you a better idea of how it integrates with Visual Studio and all those development tools. So that's the second slice, the software. So you have the hardware, then you program it, and then you get to that stage, and what you have is it works, like the camera that I showed at the beginning, but it's really. It's not something that you would want to give to someone. It's not a finished product. It's a bunch of hardware modules tied together by cables, and you can't really hold it. You can't put it in your pocket. It's not a product. It's a very rough prototype. So the next step in building prototypes is you have to give it shape. You have to give it form, and that's what this third pillar, the digital design and manufacture, deals with. Because one of the standard ways, I guess, of when you're prototyping, and a lot of people do this with Gadgeteer, is you just take all these electronics and then you take a bit of cardboard or you take some prototyping tools, whatever you have at hand, and you make holes in it and you attach them and you glue and you use sellotape and blue tack and all these things, and you can build something nice. So someone here built this interactive toy in a couple of hours using Gadgeteer and cardboard. And that's great, and for very quick prototypes, it's fine to prove a concept. But you can't really give it to anyone. It's a very fragile thing. It doesn't really look like a product, and also each one is very difficult to make. So if you wanted to make 20 of these, to give it to 20 people, it becomes very complicated. So what we're really interested in is these technologies that are more and more coming online and becoming more available, which they go by various names: rapid prototyping, rapid manufacturing, 3D printing, And the basic idea is there's a bunch of different technologies, but you design something on the computer using a computer-aided design tool. So you make a design of an object, then you feed it into this printer, a 3D printer, which will then physically construct the object for you out of plastic or out of rubber or out of metal. There's a lot of different techniques. And it's very much an automated process. You just give it the design and the machine will build whatever you tell it to build. So the output is a physical object that you hold in your hand after a couple of hours. So this is one of the sort of relatively cheap 3D printers that we use sometimes building an object. And the way that this one does it is by putting layers of plastic one on top of the other. And it'll build it very exactly to your specifications. So the interesting thing is about these technologies is they used to be only found in very sort of sophisticated prototyping labs, sort of high-end architects' bureaus and things like these. But and while the very sophisticated machines are still very expensive, they're very quickly dropping in price and becoming more available in different form factors. So at the moment you can buy like a basic 3D printer that you can use in your home for prototyping for about $1,000. And what we're seeing is, we're thinking the next 5 years, this will even drop much further in price. It's sort of companies like Hewlett-Packard is now selling a 3D printer alongside with their inkjet printers, and the laser printers is part of the range. So we expect these in the next few years to become even cheaper, more available. We're seeing them at a lot of schools. And of course, you don't need to actually have one of these machines in your home. If you have your digital design, you can send it, upload it to the web, and there's a number of services that will send you back your physical object. So that's just a little detour into 3D printing, but I just wanted to show you how we're trying to integrate that with Gadgeteer as well, because we think it's a key part of this process, this shaping, this constructing the object. So what we have done is we're building some extensions to existing 3D design tools that let you very quickly construct a custom enclosure shape for your Gadgeteer electronics. So this is a simple example where I'm starting from a template. You can create these things from scratch, but here I'm starting, I say, I want a box, and I want the box in these dimensions. Then I say, in my box, I want to have a mainboard. I want to have a button and an Ethernet connection. And it will load very accurate models of those modules into the software. Then I place them inside the box, and it will automatically generate little mounting fixtures. You can see highlighted there. It'll generate the little pillars for it to actually be held in the position that I wanted. And finally, it will make, an Ethernet connector is no good inside the box. I need to be able to access it from outside, so I can plug in the Ethernet cable. So it will automatically take into account that all these things, and will make holes and allowing that to happen. And that's the process. And then I can take the design of that box, have it printed, send it to the machine, and then a few hours later, I am holding this object in my hand, and I can put the electronics inside. And again, if you come to the demo tomorrow, I can show you a whole bunch of examples of more interesting objects than just boxes that we've built in this way. So just to tie all these things together and give you an idea of how these things will come together, I just wanted to walk you through this example, a little challenge that we set ourselves about a year ago to see if we could make a handheld gaming device in less than 24 hours. And this is the result. So we spent about 5 minutes assembling the hardware once we decided what we wanted. So we wanted a little joystick, a knob that you could turn, and a USB connector to program it, and a display. That's all we needed. So 5 minutes to assemble the hardware. Then it took about 5 hours to write and debug the code. But that's not a lot considering how complicated the game is. It has multiple states. You'll see the game at the end. It's a puzzle game, a bit like Tetris. And actually writing something like that in an embedded platform in about 5 hours, we thought was pretty good. This is just to give you a quick idea of what the code looks like. It's really sort of high-level object-oriented, and you have all these drawing primitives and things that you would expect if you were programming graphics on a computer. It took about 3 hours to design a custom enclosure. It's a bit rough. It could be smaller, but it took about 3 hours, and it was a good attempt for the prototype. So you can see the models of the various components in there and how they all fit together. What took the longest was waiting for the 3D printer to finish its job, and we sent this to the printer, and it sort of built this enclosure out of plastic. It was printing while we were doing the programming. So after that, it took about 30 minutes to assemble. Once you have to take the pieces out, you have to clean them a little bit, and then you connect you put all the electronics in. Everything fits in place, and we have little screws that everything fits tightly in place. And then, and at the end, you have a fully functional device. Can you click? Puede ser clicking? Yes. That works, and it really approaches almost a product. You can imagine someone taking this and using it, and you can give it to someone and it'll work, and it's robust, and all these things, and the case is raw. So there's a cable just giving it power at the moment. That's all that cable is doing. All the code is running under. You could add a battery and it would work. And of course the nice thing is, if we wanted to make 20 more of these to prove our concept with 20 people, we could just run the 3D printer longer and make 20 copies of it. And that's really exciting, because that's something that for us has been out of reach in the scale of how we can do prototype and how we can prove these things. So that's it. I hope that was a good overview of what Gadgeteer is and does. The best way to understand it is to come and see the demo tomorrow. To let you know, the next steps, what we're trying to do is, like I mentioned at the beginning, is we're trying to get Gadgeteer out of the lab and into the hands of other people. So the first thing that we've done is we've made everything open source, because we think that this is the best way of reaching the communities that we want. We want people to extend it, to innovate on top of it. So we've just recently in Codeplex, Gadgeteer.codeplex.com, you'll find sort of the design guidelines, hardware specifications, and the software. It's worth pointing out that .NET Micro Framework, the underlying technology, is also open source already on the Apache 2.0 license, and we're releasing everything under the same license. And there's a community site in development. There's just a place to register your interest at the moment, but that should be coming online in a couple of weeks. Just putting it in the open source domain is not going to make this a reality. So what we're doing is, at the moment, we're working very hard with a number of different hardware manufacturing partners, people that are already in the business of making hardware kits and selling them to consumers, and have all the distribution channels and everything, to actually make sure they build some kits that meet our quality expectations and our specifications. So that's what we're doing at the moment. We expect that there will be initial availability by the end of July. So there should be kits. Not all the modules that I showed you will be ready, but a considerable amount of them will be. And a lot of them will be an improvement on what we have already. So we've been going back and forth. We want to make this as cheap as possible. We expect the basic kit will be about $250. At the end, it's up to the people that sell it, but we're trying to keep those costs down, and that would include sort of the main board, a much bigger display that I showed you with a touchscreen interface, a camera, the audio module, various networking modules, and so on. And then over the course of the year, and hopefully going into the future, various different manufacturers outlets will be able to provide Gadgeteer modules. They'll just be able to include in your kit. Yeah, that's where we are at the moment. If you're interested in using .NET Gadgeteer, especially for research or for teaching, we'd love to hear from you. And that is the best email to make sure that we have a record of your interest. It's gadgeteer@microsoft.com. You can also please feel free to get in touch directly, or we can chat afterwards. Okay, Thank you very much. Muchas gracias.
Thank you, Nicholas. I think we have a couple minutes for questions.
Hi, thank you for your talk. I was wondering how you compare this with other hardware kits. There are a bunch of them around, and I knew one, Fidgets, I think, that also had a C# interface. This looks nicer, but...
Thank you very much. So there's a couple of things. I can explain the difference with Fidgets as well. One of the Fidgets, if you haven't seen it, it's a similar concept. You have hardware modules, but you plug everything into a PC via USB. So you need the PC as the center of your world. And for a lot of the devices that we imagine building, both in terms of size and cost, we wanted to move away from having a PC in the center. So the scale of it's much smaller. It's all embedded. And this idea of you have something which is 5 centimeters by 5 centimeters rather than the smallest PC. So that's one of the key features is the embeddedness. Also, there's this sort of concern with the form factor, with the shaping of the object. I think it's quite unique, and I think it's something that there's a number of different ways to execute on the electronic side, but not so much on the physical form factor. And so I think it's really sort of the combination of these three elements that makes it unique and makes it just so much more productive than other things that at least I tried. We built it not because we wanted to build it, but out of necessity. So I think we've addressed all these things. Yeah. Thanks.
I have a question.
Sure.
Let's say I build a Gadgeteer device. I want to sell it to somebody else. Is that allowed?
Absolutely, yeah. So everything is released under the Apache 2.0 license. So it's not prescriptive. It's not viral. You can do whatever you want with it. And in fact, that's what we hope happens, because I think having a toolkit like this fills a very interesting niche between sort of one-off prototypes and mass products. Sort of, and what we're seeing more and more is people, making 20 of something and then selling them over the internet. And at the moment, the kind of things that people are building are kind of jewelry or custom things, but those markets are expanding. It's the long tail of devices. And what we're hoping is that through this combination of rapid manufacturing and modular electronics and all these things will enable people to actually make sort of bespoke devices that they can. It's sort of cost-effective, both in terms of time and money, to make in low quantities and so.
That'd be great. I think this will create a lot of jobs.
Hopefully so.
Okay, so thank you again.
Thank you.
Thank you very much for inviting me. I am very happy to be in this beautiful city. It's my first time in Cartagena. In fact, my first time in Latin America. So I'm enjoying it tremendously. As Dean already mentioned, I work in Microsoft Research. My team is responsible for the Microsoft Translator product and the associated research. We are both a research team and a product team, which works well in that area because if you have used any of the translation services, you have noticed that we are far from done. So having a short path from research to product is very beneficial to us. Today I'm going to talk about how automatic translation can help encourage and empower the worldwide exchange of research papers, information, data, what have you. All right, our machine translation engine, I'm going to use the word MT from now on, MT short for machine translation. Our engine is a statistical MT engine. Statistical means it learns by itself from large amounts of data and generates models out of it. Models are algorithms that respond not with a yes and no, but with a probability. As in, this is my top answer, and I'm 60% confident, and this is my second answer, and I'm 30% confident. This is my third answer, and I'm 10% confident. So the most important data that a machine translation engine learns from is what we call parallel data. Same document in two languages. You see here a picture of the Rosetta Stone, which is the first known parallel document in existence. So today, of course, there are lots of Rosetta Stones lying around, mainly on the web, but also other sources. So this simple schematic view here is we use large amounts of parallel material and monolingual material in both source and target language. And we train the statistical models on these systems via a high-performance cluster. And then we deploy all that stuff on a web service and make it available on the internet. And we wrap some UI around it. Most simple form of UI is an API that any application can call, but there's other UI around it as well. For instance, if you go to the Bing translator site, you can copy and paste some text and have it translated. This is a more detailed and inside view into that system. So on the left side here, oops, what did I do? Okay. Anyway, I'll just talk to it. On the left side here, you see the input. This is the runtime view. Really, on the left side, you see the input. You can pass any text or a structured document like HTML or XML. What happens is that these documents are going to be parsed, and we generate some linguistic structure out of it. That helps us during the translation. For that, we use parsers that have been developed over the years, and that's available in many languages. And it gives us some linguistic information that is represented in a statistical model and helps us map the structures of source and target languages to each other. That's very helpful, particularly when translating between languages of different sentence structure or word orders. It's quite expensive to develop such a linguistic parser. And the system supports 35 languages. We don't have these parsers for each of those 35 languages, and for the rest we use a simple phrase-based model. No linguistic information, just sequences of words are mapped to each other. You see in this green box here, there is a pretty large variety of different models that are consulted during the translation process. You can imagine that if I want to gather information and want to be pretty certain that information is correct, I'm going to ask multiple people with different expertise. And I'm asking you, you give me this information, I'm asking you, you give me that information, and then over time I learn which person to trust more on a particular topic. And that happens during what we call a lambda training, so we learn how much weight we give each of these models in terms of how much we believe their answers. We call our system a linguistically informed statistical MT system. All right, this is the practical application that I wanted to get to here. There is this website called worldwidescience.org. It is run by the United States Department of Energy, and that government institution has partnered with a third-party developer and with us in providing the worldwide aspect of this. What it is it allows you to enter a query in the topic of energy research, and it hands this query to a large number of individual databases and retrieves all the scientific papers from these databases that satisfy this keyword. And to make that work, of course, these databases are located in many different countries. To make this work, you need to translate the query and the target. So you get to it by clicking on this search in your language button. Then what happens is you can choose your language, and the system asks you what is your language. In this case, I choose Portuguese. I enter a query in Portuguese. I get a number of results. So what the system did here is it took that Portuguese query and translated it into the native language of each of these databases that the system supports. And it collects all the results and ranks it in a single results list. Of course, I'm a Portuguese speaker, so I'm not understanding really the other language papers that are being presented here. So I say traducir resultados, and then I get the results in my language. Right? So let's click on the first result that is returned here. So I go to the National Library of Australia. The National Library of Australia does not publish its papers in Portuguese. I see it in Portuguese here, so we translated it in real time as the person opened that, the user opened that, the link to that paper. Here you can see the list of all the databases that the worldwidescience.org supports. Okay, a benefit of using a statistical MT system is the speed with which you can build a system. Given that you have large amounts of data to actually train the system on. We have exercised that when the earthquake in Haiti happened a little more than a year ago, a person in Microsoft's disaster response team, yes, there is such a team, called us and said, hey, what can you do? Can you help us? There are all these foreign helpers traveling to Haiti. What can you do to help them communicate with the local population? We said, no, we can't do anything because we don't have any parallel data. But it turned out we were wrong. There is quite some parallel data available between English and Haitian Creole. Also other languages in Haitian Creole, for instance French. One document that's pretty much always available in parallel form is the Bible. So that was our first training data, and the first builds of the system had a slant towards religious language, obviously, but we could fix that over time. It's still not one of our best systems, but it works in many cases. So why is Microsoft using automatic translation? So I'm talking about why Microsoft is using automatic translation for its own purposes, not necessarily considering here that the service is available for everybody to use. So Microsoft creates a lot of material in English and uses human translation to provide its products and help material and other text in other languages using human translators mostly. So as a result of it, there is not a lot of material available in all languages. Microsoft localizes some of its products into 100 languages. Obviously not everything Microsoft produces is available in 100 languages. So what I'm advertising here internally and externally is to bring a little more color into this simple red and green bar by offering. Well, the reason, of course, is that not everything is human translated. Is there's not enough money available. So offering some intermediate ways of providing somewhat lower quality translation in a larger set of languages. So you can do this, of course, with what we call raw machine translation. You publish material as it comes out of the MT engine. You can also customize the system to a certain degree by giving it training material in a certain domain. I already mentioned the Bible translation. Microsoft uses the same techniques to produce material that sounds more like it came from Microsoft and not from anywhere else. In terms of respecting the style and the terminology that is associated with it. You can use slightly edited machine translation, as in fix-up, only the egregious mistakes, and otherwise let it go. Or, of course, you can use a heavily edited machine translation. We call this post-editing, with which you get a human quality document. So there are many quality levels between no translation and fully reviewed human translation. So I call this the no translation monster, as in there's so much material that's not available in any language that it is preventing access by so many people around the world. So one example of lightly edited machine translation is the website for this meeting. If you go to it, you will see this little gadget at the top of the page, which allows, or I should say, the page is originally written in English. So there's this little gadget on the top of the page that allows visitors to translate this. Microsoft Translator supports 35 languages, but intentionally the authors of this web page have this restricted to only Spanish and Portuguese, because that's the target audience for this website. How they did it is they went to the Microsoft Translator.com website and generated a little piece of JavaScript that they pasted at the top of the page. Here they can customize it and set colors and other functionality, so that the visitors can go there. They click on translate this page. They can see it in Spanish as a result. So I don't speak Spanish, but I've been told this is a pretty good translation. Not perfect, though. There are a couple of mistakes in it. So what, in fact, any visitor can do is go to this page, hover over a piece of text that doesn't seem perfectly translated, click on this More Translations link, and see what other people have said or have suggested as a translation, and they can vote on it. If I'm a person with authority, my vote is authoritative, so it will produce it will mark that option so that it overrides the machine translation. The side effect is that the engine learns from this input, learns what are better translations and what are worse translations, so it can sort it out over time to be good. So what you can see here is that the top alternative here is what in fact my boss Alex chose as being the appropriate translation, and what you see below with that little alphabet circle icon is our original machine translation, which is which is an okay translation, but is not appropriate in this context. How does it work? The translator service includes what we call a translation memory. That is a large store of parallel sentences. And whenever it has the appropriate weight, the appropriate votes by people with authority, it will replace the automatic translation. So if you ever see that sentence again, it will apply the translation memory first, and then override the automatic translation, and for whatever does not fit, does not have a match in the translation memory, the automatic translation will be applied. So the nice thing is that it is restricted for a certain domain, in this case for this website, but it will be applied whenever the phrase appears again. The other nice thing is that it works worldwide. It's secure and reliable, doesn't go away. You don't need a local store, you don't need local memory to work with it. And the other nice thing is that the whole functionality is available through an API. You go visit api.microsofttranslator.com, and you can use all these translation and translation memory management functions the same way we do it in our widget. I want to quickly talk about another project that we have worked on together with our support organization, which shows the use of automatic translation, or the usefulness of automatic translation. This is a knowledge base article. The knowledge base is what you consult when you have a problem with your computer and try to find a solution. How most people find these solutions is through a query on a search engine, say Google or Bing. So for the most of the articles in the knowledge base are originally written in English, and then most of them are machine translated, but some of them, the most frequently viewed articles, are translated by humans. For the machine translated articles, we give a warning, as in we tell people this has been machine translated, so there are no surprises. At the end of every article, we ask, did this article help you solve your problem? That's the most important question. We wanted to, the purpose of the knowledge base is to help people solve their problems. People click yes or no. And this is what it looks like over a month, the statistical results of the answers, of the yes answer to, did this article help you solve your problem? What you can see there is not a lot of difference between so the red bar represents human translations, the green bar represents machine translation. And within each language, there's not a lot of difference between those. With a couple of exceptions here, Japanese and Korean, where there is a large difference, meaning the understandability of the machine translated articles is a lot below the human translated articles. For the other languages, that's not the case. So that's good for us, except it tells us some more work to do in Japanese and Korean. What helps the success rate here is that the English is already authored in a way that is friendly to machine translation. One more experiment here that we did, again together with our product support organization, trying to answer the question, if I look at a certain country or a certain language group, by machine translating the material in that language, do I actually increase my reach, my audience? And you guessed it, the answer is yes. So the setup of the answer of the experiment here is comparing the situation where I had only a small portion of material human translated, and then where I have everything translated, most of it being machine translated. So in October 2009, the case was that only 2.5% of the content was human translated. But those were the most frequently viewed pages in the whole knowledge base, so it covered 50% of the page views. In 2010, All of the knowledge base was translated, 2.5% human translated, 97.5% machine translated. And the result is that the audience doubled. So you attracted a lot more people. People didn't go to the English. People didn't find the translated articles. They went elsewhere. By offering the knowledge base here completely translated, we doubled the audience. Not bad. Finally, I want to list a couple of ways of how you can use our translation service. Most direct and immediate, you go visit microsofttranslator.com and you can copy and paste some text there, or you can enter a URL to any web page. If you use Internet Explorer, you can also right-click on any page that you are viewing and have it translated. Happens with our service. Or if you use Office, you can directly mark any selection of text, or say that and have that translated, or you can translate the whole document at once. Works in most Office applications. There's a bot for Windows Live Messenger that you can invite into any conversation you have, and it will simultaneously translate everything you and your conversation partner is saying. If you want to use it in your own application, you're welcome to do that. api.microsofttranslator.com is the URL at which you find information on how to do that. We offer AJAX, HTTP REST, and SOAP interfaces to suit whatever programming platform you are using. I think the coolest new integration that we are seeing is in Link 2010. It's a new version of Communicator, Office Communicator, which allows you to do a simultaneous translation of any conversations that happen using this product without polluting the main thread of the conversation. So you have a real-time view in your language, whereas the conversation happens in whatever other language it is, and you can reply in either language as you like. Most importantly, you can reply in your own language. So if you have Link 2010, I encourage you to try it out. So I hope that gave some ideas on how translation can help propagate research worldwide and encourages worldwide cooperation on research projects. Thank you very much for listening.
Thank you, Chris. The lunch starts at 1. I think we still have a couple minutes for questions. I'll start with a quick one. In your slide, you presented the knowledge-based translation. There are different languages, and there's a variation among languages. Some languages got 20-30% agreement, and another ones got 50%. Can you tell us what's the reason for that?
This is the graph I think you're talking about. I don't have a good explanation for that, and it's not explainable with computer science methods. It's probably explainable with psychology research. So what you see here is the red bar is on human translations, and it differs. And I'm quite confident it is not due to the quality or ability of the translators. They are doing all a very good job. It is a difference in the perception of the question and the cultural aspects of answering yes to a question like that. You can see that Japanese is pretty much at the low end. And that is common in these kind of surveys. Japanese rated lower. It's not really valid to compare the languages between each other. What we look at is comparing the effect of human translation and machine translation to each other, and that's what's important for us. We're not engaging in the cultural research here. Maybe somebody else is interested in doing that.
So you mentioned that you put that widget on your homepage, and that will translate the page for people, which is great. And you said that people can come in and make corrections, and then the next time that sentence is seen, it's corrected. So is it just in that web page that it's affected, or how does it affect other translations and other deployments?
It does not directly affect translation in other environments, except appearing as a suggestion. So whatever suggestion is made for a certain source sentence is shared worldwide as a suggestion. The approval is specific to your environment. In this case, the Microsoft Research Faculty Summit website, all pages of it. So once it's approved there, it's approved for all the pages and all the context that are tied together here. But in other environments, it will appear only as a suggestion. It will not be authoritative. So I say it's on a website, but in fact what you have here is an application ID that identifies this site. And you can use the same application ID for other applications you are writing. So you can use this website to collect human quality translations, and then you could go ahead and say, retranslate and republish the site yourself in Spanish, and you would transparently consume all the approved translations that have happened on this site. We call the underlying structure the collaborative translation framework, as in you are inviting your community. In this case, I invited my boss to provide the corrections. And we didn't have the time to hire a professional translator. We didn't have the money to hire a professional translator either. So maybe using your boss is not the best way to get your site translated. But you may have visitors, you may have a community, you may have a student who can help you do that, and you will get a high quality translation out of it. Whereas the student is not unhappy because they can focus on the severe mistranslations and fix only those, and the rest will be ready all the time. Another aspect of that is it's dynamic. So the site has changed over time. For instance, the speaker bios and the agenda has been updated since Alex looked at it. So the site is dynamic, and it's still available in Spanish, and it is still sufficiently correct, with, of course, the exception of the translation mistakes. But everything that Alex did has been retained through all these retranslations.
Well,